computational side. So I'll mention that again. So I want to, I thought for this session to try to wrap up our little module on representable functors as they are needed in some of our work, emphasizing points where they articulate with our work. I wanted to recap a little bit the basic understanding of representable functors, tie them in to our recently grown knowledge of profunctors, particularly the Hom profunctor, and then talk about their use computationally within Catlab, where they play really important roles. Really important roles in reasoning, really important roles in terms of the optimizations afforded within algebraic ABMs and other spheres. So it's with that idea in mind, I'd like to kind of explore the topics of representable functors a little bit more. There's so many more things that can be said about the role of category theory, but I want to really focus us on our needs. So to that end, I'm going to share my screen and we'll get off to the races. Okay. So again, I refer you to this great video by Bartosz Miliuski, where he approaches them from a programming standpoint and introduces some examples of functors that are nearly representable or are fully representable in the context of arrays or streams. But I wanted to ground us in our knowledge of profunctors. You recall the idea of a profunctor is very closely tied in with the idea of a bridge, right? If we have a profunctor from category C to category C, in general, it's from C to D. Really, we talked about how that's no more nor less than a functor from C op cross D, here C op cross C, to set. So any pair of objects in C and D, right, here C and C, has some set of bridges between them, right? There's a bridge from B to C shown in green right there, right? So for any pair of objects here, and any pair of objects over here, there's a bridge, there's a path between them. So if we picked A, for example, and D, there's a bridge here that goes A to B, B to C, and C to D. There's also another bridge or another path that goes A to B, B to B. That's with this green line, right? B to C, and C to D. And you can see there's a structure on here, right? There are these bridges like from B to C, and other things can build on them, like with pre-composing this, post-composing this onto the path from B to C, we get a path A to D. And we followed this reasoning before. And you may remember the C op here meant that we pre-compose. So if we have a map from A to B, for example, and a path C to B to C, then we get something from A to C, right? Get it from the upstream one because we have a path. We can lift this function with this with a profunctor going from B to C can be lifted with a function here from A to B to be a profunctor to give us the value for the profunctor, the set from the profunctor from A to C. And that was kind of the idea with this, right? If we had something from A to B and we had an F that was from A prime to A, from an upstream thing to A, we could get something from FAB to FA prime B. Or if we had something for G, something downstream of that latter one, we could post compose it with this arrow in D here, which just happens to be category C, to get something from B to D. So we can, if we have something from A to B, and we have something that goes B to B prime, then we can get something from A to B prime. Or lifting both of these, right? We can go from f of A comma B. That's the value of the profunctor, the set coming from the profunctor for those can give us the set coming from the profunctor for our A prime. That's upstream of A, B prime, that's downstream of B, right? That's that idea of going from this like set between B and C to something from a set of paths from A to D. Yeah. Okay. So for each of these from B to C, it gives, and for each F here from A to B and each H from here to C, it gives a path from A to D. Okay, so that was the idea with profunctors. And you recognize this as part of the general pattern of kind of how functors lift things. They lift either in a contravariant or covariant way, right? The list functor is covariant. If we have a function going from an int to a bool, say it's is prime, we can lift it to go from a list of int to a list of bools. That's covariant. By contrast, if we have a reader, it requires an environment to read off a value, and we have something that goes from an E to an E prime, it gives us something in the opposite direction. So if we have a function from E to E prime, then we can go from an F of a functor of the reader for E prime to a reader to E. It's contravariant. It goes in the opposite direction. I talked about that before, and I won't go into it here, but it's a common circumstance. When you need something of that, when you consume something of that, you have this contravariance. When you have something, a list of A, you can go to a list of A prime. It's covariant. So we talked about that before, and I'm not going to dwell on it. We also talked about envisioning profunctors in a double factorial context, in the context of, double model context, as representing like causal loop diagrams, where the Hom profunctor, the profunctor that we use all the time when reasoning about Hom sets, Hom of A comma B, meaning the set of arrows from object A to object B. Here we can have profunctors from a category C to a category C to encode like the minus links, whereas the Hom profunctors encode the plus links. That was the use with our work. So profunctors act as covariant functors with respect to this argument, contravariant with respect to the first because it consumes the thing the person needs to be at A to then get at A to get to B. And so we consume things, so we can lift things, go from A prime to A to go from A prime to B. Now, representable functors, the focus here, are functors that go from C to set. This should remind you a little bit of profunctors because they go to set over here, right? And we build them up out of reasoning about the Hom profunctor, right? This is a Hom profunctor here for category C. Maybe it's our schema category for causal loop diagrams. So maybe we have a schema category for causal loop diagrams. Let me see if I can help you remember that schema category. One of we've explored. This is in the context of Catlab here, right? Here's our schema category for causal loop diagrams, right? We have variables. We have plus links. Each plus link has a source variable, whence it comes, a target variable, whither it goes, and each minus link similarly, whence and whither. Yeah. So uh, we have maybe we have a schema, and we can think about the hom profunctor within the schema. So if we consider, for example, L plus here, right? Looking forward to my example. L plus, we could consider this to be the L plus object. This is some object in that schema, and we can consider for different objects in that schema, there's going to be, we could plug each object in and get a set. So this is a functor from C to set, right? You plug in any object in C and we get a set out. And you can plug in any morphism between those objects. Remember, this is a profunctor. So we can lift that morphism post-composing, right? To get, so if it's a morphism from B to C, then it's going to take things from paths from A to B to paths to A to C, just like we've been seeing here. So here we're dealing with the hom profunctor, right? Or the hom profunctor. Plug in any object, get a set, plug in any morphism, and it'll be a mapping between those hom sets. So again, a morphism here from B to C will give us a map from C of AB. That's some set. Give us a map, which is a function mapping the set C of AB to the function to the set C of AC. It's a function between set. It lifts that morphism in C by a functor. It lifts it into a morphism in set, which is a function. And that function, if it's a morphism from object B to object C in schema, then it will turn into a function from the set that you get by plugging in B here, this a hom set, AB, in schema C, to the hom set AC. So that looks something like this, right? So here's our contravariant function. This is like the view of the world from A in our schema category. Maybe this is L plus. And it has arrows going out of it to different objects, right? Right? That's what we have. Arrows going out of it to different objects. That's these arrows going out. And this is a functor. It's a functor from objects in C to sets, and morphisms in C to morphisms between sets, namely functions between sets, between those hom sets. So plug in any object, you get a hom set. Plug in any object B, I get a hom set. Okay, so plug in any object here. L plus. Okay, so this is, I'm going to have C, that's my schema category. A is going to be L plus. Okay, so here's L plus. Plug in any object. V, I'm going to plug in V. Well, what do I get? I get the hom set from L plus to V. There's two of them, source plus, target plus. That's the hom set. Subsize 2, right? Right? It's a hom set. C L plus V is a set. The set. Okay. Now, suppose I have a map from one of these objects, V. Oh, this is going to be boring. If I had a map from V to label or something to another set, which I don't have, to another object, then if I had a morphism in C, like this one, from this other object, so here's my maps from like L plus to V. If I had a morphism in this schema, had I a morphism that goes from the vertex to a label set, okay, here's the label set here, then this lifting of this functor can lift this morphism in C, could lift it to indeed be a function, a morphism in set from CAB, that's this one here, CL plus V, to CL plus label. That's a hum set too. So in short, this, each of these objects here gets turned into a set, the hum set, right? Each object here, you plug it in here. So how to put it? Each object, like B, gets turned into a hum set. The view of B from A, that's this hum set, JHG. Plug in any object here, you get a hum set. Plug in any object here, you get a hum set. Plug in L plus, you get the identity hum set. Plug in V, you get a hum set C L plus V, which is just source plus target plus, right? And if you plug in L minus, I'll get an empty hum set, right? You could have an empty hum set. And as a profunctor, it can lift any morphism here from, say, B to C to go to give us, just per this, if we have a hum set from A to B, and we have a function that goes from B to B prime, B to B, say B to C, then it turns in to a map of sets from CAB to CAC. From FAB to FAC. In other words, from the set of hum arrows from A to B, from this set of hum arrows from A to B, here, this set here, that's exactly what this is, CAB, map this object into this hum arrows from A to this thing. And this morphism from B to C gets turned into a map for each of those hum arrows. It turns it into a map from A to C, a function or a morphism from A to C. Because this F goes from B to C, it turns a CAB. When you lift it, it turns a CAB into a CAC. So this is the role of the hum profunctor from a particular object, fixed object, gives this view of the world from that object. You plug in any object here, you get the hum set from A to it. You plug in any morphism here from an object B to an object C, you get a map from CAB to CAC. That's exactly what's going on here. So that's how these representable functors work. These representable functors may seem very arbitrary, but they're wonderful to building blocks. It cannot be overstated that by specifying a single piece of information for this category, along with this category, a single object A, we specified a whole functor, right? All we have to do is say, okay, the representable functor for A with respect to this category, and we'll get a functor out. Plug in any object, get a set, plug any morphism in the category, you'll get a map between the corresponding hum sets. That's a functor. That's pretty amazing. But other functors can be described as sums of representables. In poly, the category poly, we have these polynomial functors that are built up of sums of representables, which is an incredibly powerful subset of all functors. Um, and so they play this kind of role of building blocks, the natural building blocks by which we cleave up the world, which we build more powerful functors. They bundle together things that kind of go together. And they're the roots of a lot of optimizations that we can use, because they capture what goes together and they can rule out, like for algebraic APMs, by reasoning about representables, we can rule out the existence of certain things that we'd otherwise have to search for. We can know there are none of them, for example. And the Oneida lemma is this profound, deep, but foundational result within category theory that remarkably relates maps between presheaves to maps between CSATs, as it were, to maps between objects. And it has great significance for programming and optimization, etc. We will come back to that in a later lecture, but first I want to give you this computational view of these things, right? Because they turn out to be very, very useful. And some of you will remember some kind of things we've written with perhaps without knowing them about them in detail, but might now start to make sense. So I'm going to open up here a few of these examples that we had in class during our previous term. And we're going to use them to talk about representable functors in practice in our CSATs, okay? So I've been using, by way to kind of motivate and situate us here, to situate us in a particular context, I've been using this schema, right, for causal loop diagrams. You'll recognize them. Vertices, right? Here are the variables, here are the plus links and the minus links, right? Familiar stuff. And what I'm going to do is I'm going to compute the representables on here. And you'll see that there, as often happens in category theory, it makes sense. It's a very sensible concept that maybe you had at some inchoate level, but never really formalized. The representables are your friends. They're things you kind of knew about, but never really thought too much about, perhaps didn't realize their significance. So what I'm going to do is I'm going to compute the representables, and to do it, I have to load in algebraic rewriting, because that provides what's called a function that computes the representables called Oneida cache. Some of you may remember this. We use this, and I kind of mumbled about it. And I may have even said it computes representables without really telling you what those are, without cluing you in what those are. But we call that, and if you call it the first time, it will take a while. You notice I call it on the AC set type. So I declare the schema, and I declare the atchit for this, the type that involves a mapping from the schema to set. There we go. And I call Oneida cache, and it will take 2 minutes, something like that, maybe. In the minute, on the order of minutes. Now, having done that, I get a really slick thing. I get the ability to ask about representables. So I could say, hey, Catlab, tell me the representable functor for L plus. Tell me the representable functor from L plus. Tell me about the world. from the viewpoint of L plus, right? I'm talking about this, right? Tell me about the world as it looks like from L plus. So I'm asking it, tell me about this representable. It's a representable functor, right? Plug in any object here, you get a set. It's a representable functor from category C to set. Plug in any object here, you get a set. You plug in any morphism here in category C in the schema, and you get a map between those home sets. Okay. So I can ask, tell me the representable from L plus, and it says, yep, I'll do it. And it gives us the representable. Okay. So here we have the representable for us. So this representable, well, you tell me. I've told you, but you tell me back. The representable for this is a what? What is this? The representable, like, what sort of thing is what sort of thing is this? I told you it's a functor. It's a functor from what to what? You remind me. A functor from what to what? It's really important to be clear about this. This is a functor from what to what?
Is this from C off to set?
Okay, from C
to set.
Yeah. Okay. Yeah, you could say it's from C up to set. That would be that actually it's from C to set because it's contravariant in its first argument. Where this is a fixed thing here. A is fixed. So that's a given. So all we're plugging in is this one, and that's covariant, remember. It's covariant with respect to its second argument. Remember that? It extends downstream with respect to its second argument as a profunctor, right? Downstream. It's not up. It's kind of like this we already specified as A. So we're not lifting that it's to anything. We're just lifting things here, and it's C to set. So it's a C set. What is C here? What is C? C is this, right? What is a C set of this? It's a what? It has 3 words in it. The middle word is loop. What's a C set of this?
Causal loop.
It's a causal loop diagram, right? The representable is a causal loop diagram. And I've drawn it here. In its crude form, I've drawn this category of elements. It has a plus link from one object to another, from object 2 to object 1. There are 2 vertices, vertex 1, vertex 2, and 1 plus link. So this isn't an awfully nice causal loop diagram to draw, but it's basically a link from one object to another. That's the representable for plus. I want you to reason this thing through. Like, why isn't the representable for plus just a, so why does it have, you tell me, why does it have 2? Why do I say its value for V why is it, if this is L plus, why is it when we plug in V, we get 2? Let's trace it through. What happens when I plug in V for 2, and you can assume L is L plus? Why is the value of this of size 2? In other words, why is this 2 here? Because what? What is it about this structure that makes it 2?
I didn't understand your question because we tell
I'm
is
I'm
a home functor,
yes.
and for example home functor X or A or something like that
Well, I'm
is
asking.
art isomorph
I'm
in and
yeah. I
is
asked.
isomorphism.
Okay, but yeah, you maybe saying something correct, but I'm asking for the representable for L plus here. That's what I'm asking about. Now I'm asking, why is the representable for L plus have a value of 2? Um, why is the set uh that it has for V of size 2? Why is this of size 2? That's what this means. This is of size 2. This is of size 1. This is of size 0. I want you to be able to understand where those numbers came from. Why is this? We're viewing the world from L plus. This was viewing the world from A, and I've just made this L plus. C is our particular schema. Hmm? So we're viewing the world from L plus in our schema. And I'm saying, why is this 2? Can you write this out for me? What is this? What is this set, right? So this is a Hom functor,
Home functor.
right? This is a Hom functor I'm asking about, a Hom profunctor. This is a fixed argument. That's a given. And we can plug in any other object here. And that's what we're going to focus on here. We're going to plug in an object, V. What does it give us? What's the
Give
value
us
of that?
the arrows between L plus and V.
Exactly. Exactly. That's why it's of size 2, right? That's why this is 2, not 1 or something. Because it's that number of arrows there. That's what that means. That's why B here gets mapped to CAB, which is of 3 things, because there's 3 arrows from A to B, right? B, when I plug it in here, the functor maps it to a set, CAB. It consists of 3 things. The arrows from A, the designated object that we're representing, A. So this is the given, to the object we plug in, B. And here, so this is the view of the world from A within category C. This is the view of the world from L plus within category schema primitive causal loop diagram 1. I plug in an object. I get the view of that object from L plus, which here consists of two arrows, right? 2 morphisms. This is just a hum set from L plus to V, right? That's what that is, a hum set, these 2 arrows. So let's expand on this more. If I do this from L plus to L plus, what is that? You tell me, what is it? What goes here?
0.
Is it 0?
Identity, right?
It's identity. Identity on L plus, right? On identity on L plus. It's the identity morphism. Remember, every object has an identity morphism. This is human is an object. V is an object. Or sorry, L plus is an object. So it's the identity on L plus. Every object has a morphism to itself. Hmm?
Yeah, source and target are equal.
The source and target. Well, and you're not dealing with source and target here. You're dealing with V. V is an object. This is a graph of 2 different objects, and there's a morphism here. So from V to itself, there's a morphism. In every category, every object has a morphism to itself. That's the identity. It's guaranteed to have that by being a category. So it's not like we have to worry about source and target. Those go between L plus and V. It's, every object has an identity morphism to itself. Are we comfortable with that? That's why
Yes.
L plus is 1, right?
Yeah.
Are we okay with that?
Yes.
Okay. And you tell me, what is this to L minus? What is this? What is that? What's the Hom set from L plus to L minus? It's of size what? It's of size. It's a very.
Should be empty. Should be empty, right?
It's empty
Empty because
because there's no morphisms going.
no morphism.
You see that? That's
Yeah,
where
yeah.
it come from. So there's two vertices. One plus link is the representable for this. The representable is a causal loop diagram with two objects and a link and a plus link from one to the other. That's one of the building blocks of a causal loop diagram. And you could say, well, wait a minute, why can't it just be a link? Well, a link can't exist without a source and a target. And it doesn't make sense if you think about it. Try to imagine this as a C set where you have one L plus, right? L plus is the set 1. And you have an empty set for V. V maps. So imagine a C set where L plus maps over to the set 1, singleton set. 1 L plus, 1 link. V maps over to the empty set. Is that possible? Is that a legit C set? Remember, these are functions. So is that a legit C set where this is the object of size 1 and this is the object of size 0? And is there a function that goes from an object of size 1 to an object of size 0?
No.
No. There's no
There
such
is no
function.
one. No.
That can't be. It's not, it violates the rules of a function. A function has to, for every one of its domain, every element in its domain, the sole L plus, it has to assign an image, right? An element of its codomain. There is no element of the codomain if V is empty set. And so this cannot be a function. You cannot have a function from a singleton set to an empty set. So you can't build, you cannot, let me emphasize this really clear. You cannot build a causal loop diagram out of a piece that's just a disconnected plus link with no source and no target. That's not a valid building block. It would not be a valid C set because you cannot have a C set with one of these, a set of size 1 for L plus and a set of size 0 for V. That's not a legitimate C set. It would violate the rules of what a function is between these sets. So you can't build that C set. Do you understand that point? Do you get that point?
Yeah, exactly.
You cannot have a valid C set with just a disconnected link with no source and no target. It's not a legitimate C set. It violates the rules of a C set because these will not be functions because they would have to go from a singleton set to an empty set. Does that make sense?
Yes.
You get that
Yes.
point, folks?
Yes.
Okay. Does anyone want me to emphasize that more? Because I'm happy to. It's a foundational building block. I'm sorry, it's a foundational point. If no one's going to ask me, I'm going to just say, you understand my point then. If you understand that, you understand closer why representables are the natural building blocks. They're the minimalist building blocks. You can't have an L plus without having a source target link. without having vertices, variables that they go to and come from. This is our minimum building block. This is the minimum block.
Having source target variables are essential for minimum
Yes.
minimum doing that.
Yes.
Is
Yes.
a good is a main point for that.
Point here. So
Yeah.
the representables give us like the minimum building blocks to build an L plus. You need a source and a target vertex, right? By contrast, for V, what's its representable? V, what is its representable? Here's V. The world from V. What is its representable? What's V? You tell me. You tell me. I'll list it up here. What is this to? I gotta put this like this, and I'll put it like this. We'll have little question marks here, and you'll fill this in for me. I know you will. Okay. So you tell me, what is, well, you start with the easier one. What's V comma V? What is this?
Identity, nothing.
Yes, identity on V, right? Or we could just write it like that, right? Are we comfortable with that?
Yes.
It's an object. It always has an identity arrow, and it's not like there's some other, other non-identity one from it to itself. What is V to L plus? What is that?
Empty.
Empty set.
Because we can't do from 0 to
No morphisms from V to L.
no more to that. Yeah.
Well, how about V to L minus?
The same as a
Empty set.
Yeah, it's empty.
empty, same.
Okay. So then you'll understand why if I say representable of V here, and I add it in here, it'll say it consists of a V by itself and nothing else. That's a perfectly legitimate C set. Here, we couldn't have an L plus without having a source and target for it. We needed it, and the same thing with L minus, right? If I did this for L minus, you could tell me what would this be for L minus?
That is same as L plus.
Exactly. Exactly. It needs its. It
Is
needs
essential.
it needs its the variables on either side of it, and if we were to illustrate it here, it would be like this. But meanwhile, for V, you could just build it by itself. It doesn't have any dependencies. There's nothing it needs to be built, right? It doesn't need to come along with other things. Do you get that point?
Yes, that is clear. Thank you.
So these are the kind of natural building blocks. You could think, well, a plus link is a natural building block, but no, wait a minute. It's not a self-contained building block. It's not a complete building block. It's not a legitimate C set after all. You cannot have a C set where this is a singleton and this is empty, because that will not be a legitimate C set because these won't be functions. And it turns out this point is really valuable to know. And I'd say it's very important to know when you're using algebraic rewriting, is to know what's a legitimate C set and what's not. So having gone through that, with you having graduated from this, now we could do algebraic ABMs. Here we go. Oh no. Algebraic. So why can't I? Algebraic rewriting. Rewriting. Sorry about that. And timer's running down. So rewriting Happy, happy. So here's a simple little APM, a simple little schema. We'll visualize it. This one's a little bit more textured than our last one. And you're going to tell me what the representables are for this ABM. So I'm going to execute this, and oh, look at that, look at that. So I'm going to do a UNATA cache on this AC set type, and while it computes, you're gonna muse about what those representables are. So let's start with a simple one. What's the representable for province?
Identity.
Identity, because like a V.
Yeah, it's of size 1, and it contains just the identity. So it's representable for province. Let's be clear, though. Representable for province is a functor, which it's a functor. If so it's a functor. So it's the view of the world from province. So if you plug in any object, it will give you a set. So I'll plug in province, comma province. It gives me a set of size 1, which is province. Plug in province, comma person. What is the size of that set?
0.
0.
Province, comma dog. What's the size of that set?
0.
0.
Province and age group. What's the size of that set?
0.
0.
Good. Okay. Now let's get a little bit. Okay. How about for age group?
Same thing.
1.
Mutatis mutandis.
1.
Yeah.
From
Identity.
age group to age group, you plug in
Identity.
the view of the world from age group. So you plug in age group with itself, you get something of size 1. Age group with province, you get something of size 0. Person, set of size 0. No. Okay. Now you're going to tell me, though, what is the representable for person? So let's go. I'm going to copy the code here, and we're going to apply it here. But meanwhile, you're going to tell me, you're going to muse about it. What do you think the representable is for person?
2.
Okay, so we're going to do the representable. Oh, here we go. The representable for person is, you said 2, but, right? So a person to be built, you cannot have a person in isolation of a province. Why not? Why can't you have a person in no provinces?
Because every person has a province.
Every person is a province. Every person, there needs to be a function from person to province. If you have one, the representable is going to have one person here, and you need at least one province for them to be assigned to it. And same thing for age group. There needs to be at least one age group for that person, that single person, to have an age group. Otherwise, it won't be a C set. There won't be a legitimate C set. There'll be an illegitimate map from this to this, because you can't have a map from a singleton set to an empty set. So the minimum building block has to consist here of person, province, and age group. And indeed, that's what we get. A person, age group, and province. Those are needed to build a person. To build a person, you have to have at least one age group and one province. Do you need a dog?
No.
To build
No.
the person?
No. Every dog needs one person.
Okay. So the representable for dog, what is that going to consist of?
Just person. Or just 1 to person, 0 to everything else.
Yeah. Every dog needs a person.
Okay, but to get a person, don't you need something else?
Yes. Province and
Province and
age.
age group.
Yeah, so you're going to need a province
Oh,
age group.
Oh,
The
3.
compose, right?
So,
right. Yeah, because composed arrows.
Yeah,
compose together.
exactly.
Yeah.
Exactly. So you need
Yeah.
a person, a dog, a province, and age group. And that is a natural building block. if you're going to have a dog, you need the person, and you need the age group for the person, and you need the province. If you just have a province, you don't need the person, you don't need the age group, you don't need a dog, and I think you get the point. These
Yeah.
are natural building blocks of this, the C sets here. The C sets come as with these building blocks. Each C set is built out of these building blocks. You might think there's a C set that has a person and nothing else, but that won't be the case. Or a dog and nothing else. That's not a legitimate C set. All C sets are built out of these representable things, these things that can actually be represented, be built. And those are not just the pieces in isolation. Those come in, pieces that are mutually consistent with each other, that can go together. Now, we've run out of time, but I will just note that if there were self arrows from person to itself, for example, other than the identity, then that would also be a need that would that might require not just it. So you'd have to ensure that that if let's suppose person has a self arrow identity, and then it has mother, and then it has father, self arrow, person to person, right? You could think about what's the building block from person to person. You tell me, right? If I, what's that?
Infinite recursion?
Well, let's think about it.
So like my grandparents all have grandparents, and I mean, unless we're considering Adam and Eve or something, they're all gonna continue having grandparents, even if it's like a Homo erectus or something.
Yes, your span of disciplines there is impressive. Uh, uh, so I'm going to share my screen here, and I'm playing hooky here, but I'll to good effect. Okay, so ABM challenge, and then I have this, and maybe I have a person. So I have a mother from person to person. I have a father from person to person, but I have no, implicitly, there's identity from person to person, right? Because every object has identity. So I'm gonna put this here, and then I'm going to declare an atchit, an AC set for it. Here we go. And here's our little challenge. And I'm gonna do it ABM challenge instance. And I won't bother doing the index. Okay. And now I could ask, what's its representable? And there's an interesting question, but I have to do its UNATA, right? And Evan has got me wondering if a Homo erectus is gonna walk out of the computer here. Okay, wait a minute. Where'd I go? Okay, here we go. UNATA cache for this. Okay, let the Habeline computations begin. So you tell me, think about it. So if we're viewing the world from person, and I plug in person here, what will that set be? What would that set be? If I have C, that's my schema here. I have person as A, the fixed object, and I'm viewing the world from person. and I plug in person as the object here. What is this schema? Person, comma, person. What's the HOM of person, comma, person? How big is that? Size what?
3.
Size 3. That's right. How big is the person? How about person to dog? How big is that?
0.
Still,
0, because
that's right. It's still 0. How big is person to province?
just 1.
1.
Just 1.
And age group is 1 as well. Because
Group is 1. So here we're going to ask for person to person, right? And okay, so this is okay. So what's going on here? This doesn't. Oh, I know. Cash. Cash equals. What do you do? False. False. Is it false? Capital F.
I think it's lowercase.
But is this the name of the extra argument? I'm trying to remember. Clear. I can't remember. Does anyone know how to get the what is it? Clear cache or something? And you remember the name of the argument, the extra argument here?
It's clear equals true, I think.
Like
The arguments are type, clear is a Boolean, and cache is a string.
I see. Okay. Mumble. Okay. Okay. So like, this you're saying, Eric?
Yeah, I think that's right.
Okay. And now we could ask for the representative. Okay, so this doesn't make sense here because I would have expected for the representable for person, it would have been 3, right? The identity, mother, and father, right? So that's something that I am not okay. So let me just do with representables. Okay. Maybe I'll duplicate this. Mumble. I guess I can't. Okay. Yeah. I would have thought that okay, I'm gonna probably I shouldn't do it this way. Can I like restart the kernel or something or
Yeah, there's a restart kernel and run all cells is an option under run and under kernel.
Restart kernel? Yeah, I'll just restart. Okay, fine. And I want to make sure it's not kernel unknown. Okay. I'm
it just takes a second. Yeah.
And I just want to use it. Unata cache. Oh, okay. That's not what I want. I want to just do it for this one. And mumble. Here we go. Yeah. Okay. AC set. Unata. Oh, I see. That's the mistake. See, I said simple AB.
Oh, yeah.
That's why. Okay. Unata cache clear equals true. It's going to crunch for a while. It's computing all the representables here.
So my question is still the same point about the Homo erectus is if we decided, I mean, we saw earlier that in dog it has 1 to everything because we have those composite arrows. So what would be stopping, like when you're trying to make an instance of this C set, how would you do it without having infinite people? Because if you have composite arrows, then theoretically there's an infinite number of composite arrows going down forever.
This is okay. So yeah, because you're saying it's a free schema. And so for each iteration of mother, 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 there's a separate arrow conceptually. It's because it's a free category, a category freely presented by the schema. It's not going to converge. And so there's an unlimited number, an unbounded number of arrows for this. And I think Eric is actually right. I think what we are seeing is if we wait for this, we may surpass the number of years since Homo erectus walked the earth.
Well, I presume that they would have come up with a workaround for that or something, but yeah, we might be here a while.
Here, do you mean topos?
Topos, yeah.
Yeah. I actually think that these self arrows that can lead to unbounded number of compositions in a free way. I do actually think this is an issue. Now, one thing you could do is you can impose, when you have a schema, you can impose equations on that schema that specify equational constraints, like my mother's mother is equal to the identity or some weird thing like that. But
I suppose you could also maybe add an unperson to the person set who just kind of counts as a null value, although that might make other things in the model weird to think about.
Yeah. Yeah, I think this is actually I think it is actually an issue when you have when you have it unbounded freely like this. Yeah, I think it's I think it is an issue. I think I remember Chris Brown mentioning it as a concern, and I think it's evidenced by the fact it's not converging here. So here the representables are not calculable, using simple the algorithm that it used to enumerate them, because there's an unbounded number of compositions. I suspect it will eventually probably exceed some stack depth or something, and it will say, representables could not be identified or something like that. But I do think it comes in. So just be aware that there can be, when you have these loops, these issues with representables. So I want to tie this in with one other point, because we've been talking about Catlab and algebraic ABMs, and also has been a substantial point of discussion in our group. I want to point out this issue of not a valid C set, which I spoke about, is an, oh yeah, I should also mention a C set colim. You may recall this idea that you can use a C set colim to specify C sets which exhibit certain properties. And you can declaratively specify them. So here we have a sheep and wolf that are in the same location. You may remember that. from our algebraic ABMs exploration, to which we'll be getting back as the update to Catlab finishes. This huge update. This is based on representables. This is based on this ability to specify representables, and that's why you have to call UNADA cache before this to compute the representables. And these AC set columns are built up out of representables. The representables are the building blocks of C sets, of legitimate C sets. And you may not recall there was an issue with legitimate C sets right here, in fact, that if we had, for example, a person and they were in a certain location on a graph, and maybe there's a name and a social security number or something, and we wanted to rewrite them to be on the distal end of an edge. So they're at the starting end of an edge, and now they traverse that edge. This is a C set. It's a valid C set. They have a location. This is a valid C set. They have a location. This is not a valid C set because there's a person, but not a map to a vertex. There's no function from that person to the vertex. So this is not, in fact, a legitimate C set because there's no map for this person to a specific vertex. And this issue of you can't assume that any randomly instantiated sets for, an arbitrary set for each object in the schema is a legitimate C set. It may not be. For example, it's not legitimate to make this empty set and make this non-empty. They go together, and that's the idea of representables. They go together, right? The building blocks do not include a person without any possible vertices. For there to be a person, there needs to be at least one vertex. And so representables give you this kind of minimum legitimate C set, which is not to be assumed. If you just splat down data of arbitrary sets in a C set database, you will not have a legitimate C set in general. You'll have an illegitimate. It won't be a legitimate C set. And so representables give us this ability to specify, the natural, consistent building blocks in the form of Z sets. But they have their limits. You can see the UNADA cache, Eric, is chasing Homo erecti across the savannah. And I don't think it will return anytime soon. Okay. So that's all we have time for today. I got to get to this other meeting on our app about to be launched. But it's great to be talking today. And I hope that gives you, that two-part module gives you some sense of representable functors, both, as building on the knowledge of pro-functors, as they describe a representable. And remember, representables include not just those built up that way, but things isomorphic to them. So functors that are isomorphic to them, I think is the right way to say it. And we also talked about their computational instantiation. We will soon see within probably the next month or two why they're so useful for optimization. To understand that, we'll probably have to go to the UNADA lemma and talk about the amazing insights that can be offered through UNADA lemma and why it can provide real value computationally and real efficiencies in your reasoning. by capturing the deep relationship between morphisms on the one hand and pre-sheaf on the other. Okay, that's all we have time for today. Thank you, everyone. Take care.